Hello and welcome to another Tech Day. If you don't know what this is, it's a daily. I hope to make the daily episode. I'm not succeeded at it, but it's a daily episode in which I'm learning all the necessary technology that is required for me to make the next step in my career. So today, just a second, I would like to apologize if you hear any rumbling in the background. We just got a cat and he has a case of zoomies. Actually, he's right next to me at this moment, but at any other one he can just go wild. As you already know, there's my trusty tablet, which I'm gonna show you in a moment. Wait, here it is. My trusty tablet. Yeah, it's 11:55. It's quite late. I should have done this earlier, but sometimes I just don't have time. So I'm gonna consider this one come the day afterwards. So instead of September 27th, it's gonna be September 28th. Oh, what's this? Auto format, summarize, translate, and sketch to image. Who is sending messages at 11 o'clock? So tech day, tech day, tech day. What are we doing? Oh, okay. Section that I hope won't be lasting longer than 30 minutes will be on the topic of booting the Linux device. Booting process. I just realized boot as in powering on me is similar to the word booty as in someone's bosoms, but okay, not important. The booting process in the context of the Linux machine is the sequence of steps that starts with us powering our machine and ends with us getting the graphical user interface of our operating system. So from powering the machine to getting the GUI. It's a close environment of different components working together: hardware, firmware, bootloaders, and the operating system itself. Now we have a couple of different stages or steps, and the first one is, first of all, I I won't be able to reproduce this because logically I wouldn't be able to share this. But let me try if I can Google and find some picture. Booting Linux up. Booting Linux up with images. Let's see if we find something. Okay, so this is a 2016 article. There's a boot here. Understanding the Linux boot and startup process is important to being able to both configure Linux and to resolving startup issues. This article presents an overview of the boot up sequence using the grab2 bootloader and the startup sequence as performed by the system deinitialization. Initially, what? I don't know how to speak English again. Initialization system. So there are two sequences of events that are required to boot a Linux computer and make it usable: boot and startup. The boot sequence starts when the computer is turned on and is completed when the kernel is initialized and systemd is launched. The startup process then takes over and finishes the task of getting the Linux computer into an operational state. Okay, do we have images? No. I would like to have... Oh, man. I mean, I love this, but I would prefer I would prefer to see it visually. That's why I wrote booting up boot Linux explained. Step-by-step guide. Why is this happening? So if I move my mouse somewhere, it seems if I move it to this corner right here. Stupid. 6 stages of Linux boot. The thing is, fuck! Is this serious? First of all, I need to disable this minimizing of my Windows. My notes for understanding the Linux boot process. Oh, okay, so this has some images here. What the hell, man? All right. First of all, let me disable this. So this thing here is called hot corner feature in Ubuntu, Pop! OS, or at Fedora, all of the GNOME-based desktop environments. So how do I disable it? I need to install tweaks, and the good thing is I already have tweaks here. Top bar or general? Hot corners. Hot scrolling method. What's this? I don't care. Windows. Keyboard appearance. Fonts. So I don't see anything here. I don't see anything here. This is so stupid. Window action key, attach model dialogues. Is there another way? So I can also disable it via the command line. This works immediately. I would need to restart if I was using tweaks. Okay, so let's do this other version. New window. Let me move this guy here. G settings set org GNOME desktop interface enable hot corners false. All right. Wow. Thank you so much. So let's do this. So let's now do this. When was this written? July 3rd, 2024. Right. Power on and hardware initialization. Again, I'm having trouble. Power on self-test or post. The power on button triggers the system to start the CPU cycles. The CPU has a special register called the instruction pointer or program counter, which holds the memory address of the next instruction to be executed. The power on button triggers the system to start the CPU cycles. Alright. So it has a special register called the instruction pointer or the program counter. And when the system is powered on, the instruction pointer is set to a default memory address known as the reset vector. This reset vector typically points to the read-only memory. So instruction pointer or program counter. instruction pointer or program counter. So this should be the same thing, right? Let's see, do we have any images? Program counter. So the program counter holds the address of the next instruction, ensures the CPU knows where to continue execution. Automatically increment to the point to the next instructions. So wait, is there any basic difference? They are the same thing. So this is good to know. This would be confusing in any other scenario. So I don't want to go a lot into details. I could actually there's a way to reproduce this by and to observe this by installing the virtual machine Kimu. I don't know how do you say it. It's Kimu. Quick emulator. All right, I could install this and I could see what happens at the reset vector. I could create a minimal bootloader and then I could run it. Yeah, why not do this? Why not do this? This should be funny and interesting. This should be funny and interesting. So let's do this. Instruction pointer. What is the instruction pointer? What is the instruction pointer? Pointer or the program counter? Okay, this is not it. The program counter, commonly called instruction pointer, is a processor register that indicates where a computer is in a program sequence. Ooh, actually, I want to let me bookmark this because one of the things they want me to do in my company is to transition into the position of a reverse engineer. So, wow, I don't. It's this is so cool that I found this while searching. What? Reverse engineering for everyone. This looks really interesting. So, special register called instruction pointer. Okay. So let's open new window. Let me go and install sudo apt install Kimu system x86. Do you want to continue? Yeah. So we have this installed, 99, bam, done. Amazing. Let me go here. So I had some issues. I think it's okay now. Is this centered again? Most probably not. All right. Before I continue, I wanted to do a quick recap on what some of the concepts I'm going to mention are. So one of the concepts we're going to mention are registers. Registers are tiny, fast memory cells that live inside the CPU itself. And they can hold a pretty small piece of data, like a number, like a memory address, or a flag, true or false. and they are used to execute instructions efficiently without constantly asking RAM. So I'm just gonna write here. Wait. Tiny, fast memory cells in CPU. Some registers are the instruction pointer, such as the instruction pointer or the program counter, which is one special register that the CPU uses in order to know what to do next. It's similar to an index or a bookmark in a book. It tells the CPU where in the memory the next instruction is. And every CPU cycle, the CPU reads the memory at address stored in the IP, it executes the instruction found there, and then it moves the IP to point to the next instruction. What else did we mention? Points, I'm just gonna write here. Points to the next instruction. Can I fit it? I did fit it. The reset vector is the next concept. Reset vector. So let's say we press on the power button. The CPU needs a starting point. So the reset vector, it's a special fixed memory address that it's hard coded into the CPU. And it's the place at which the flow of the computer booting up starts. Or it tells the computer where to start executing. What else do we have? What other concept? ROM. ROM is the read-only memory. It's a chip on our motherboard that contains startup code that never changes. It's like you tattoo your information about yourself on your forehead. You can't erase. I mean, you can't. You can erase it if you go to a tattoo removal clinic or whatever. But it's there. It's something that is yours. It tells the information about yourself. For example, the things that are living in the ROM are the BIOS, the first stage boot instructions. So basically how it all works step by step. Let's say we press the power button, and the power button looks like this on most computers. So the CPU, once it clicks the power button, it gets the power and it activates the instruction pointer. And the instruction pointer is set to the reset vector, and the reset vector points to the ROM. And the ROM contains all of these BIOS and bootstrapping instructions, setting up RAM, setting up the devices, a keyboard, GPU, whatever, and then ROM loads the bootloader. And now we can start our, I don't know, Linux specific or any other specific boot process. So let's see here. No. Do I have chemo? I do have chemo. All right. So I'm gonna say here code. Let me open this in Visual Studio Code. So this is an empty. If I do new file, can I just create a new file? Yeah, like this. And I'm gonna create a bootloader, boot ASM. So can I copy this? And now let's compile and run. Let's see what happens. Boot ASM, boot bin. Oh shit, we need to install. And now, all right, what do I have here? I have the boot bin. Now, system x86 64 format and file boot bin. Okay, so what's happening here? Let's break down the assembly first. Here we are telling the assembler we are writing 16-bit code. And the second directive tells the assembler pretend that the code will be loaded into the memory address at this exact point. Because the BIOS is loading bootloaders from disk into this memory location. If I Google this one, by the way, I know that I will often go on a tangent, or I will talk about a completely separate concept. I hope that's not a problem, because it follows my stream of consciousness, or the way I kind of connect the dots here. And it says, why do we need this? Why do we need? Why is this for? Wait, why is this? I can select it. I thought this was like this is a link. All right, so this is a link. All right. So this is needed to tell the assembler that this is the load address. If you don't do this, it assumes that the load address is 0x0000. If you have the following code, you can disassemble easily the first part of boot bin to see what happens. So this is the same declarations that we have in our script here with the bits and org. The only difference is that the order is inversed. But here it says, assemble with the command that we assembled as well. You can disassemble easily the first part of boot bin to see what happens. Run this command and see the results. So this is the disassembled script right here. In the meantime, far jumps absolute jumps to edges. The org directive tells the assembler to add the org origin value to the offset. Interesting. So what else do we have here? Let's continue analyzing the script here. this line here, it sets up the BIOS interrupt at 0.10. Move. All right, so this one says I want to print a character on the screen, and this one loads this character into this register right here. And this one right here is a software interrupt. It calls a BIOS function, a BIOS or a BIOS. In this case, it says, all right, print this guy to the screen. This creates an infinite loop, like similar like we have while true. So what is this one doing? No idea. Okay, so this pads the file with zeros up to 510 bytes. Right, and this writes the magic number at the end of the file because BIOS will only execute code if it BIOS will only execute code if it ends with this magic number. And then the two commands that we did here are the and the two commands that we run here are compiling our source file into a file called boot.bin, which creates a byte file of 512 bytes. And it mimics what would be the first sector of a bootable disk. This command right here is going to run a virtual x86 machine. We are using our boot.bin file here. Wait. So the ROM generally contains either BIOS or UEFI. Wait, let me just see something else. So this makes sense. Here we set up. Here we have set up. This is a predefined, I think, output function which prints one character to the screen in this register, and this register we print this specific character. And this is an interrupt, a BIOS interrupt that is related to video services, and they are something like API calls to the firmware. And this one is gonna call the video service, is gonna call it on this from this register. And no, sorry. Yeah, this is interrupt, and it's gonna print this register, but this command here will tell, okay, you need to print a register. So we start from here after we interrupt it. We start, I mean, we don't start from here technically in our mind. When we want to understand, we start from here. Print this. We need to print a function. What function are we printing? This one. Okay, now we can go further. Let's see what else we have. This ROM generally contains either BIOS or UEFI. The CPU firmware is programmed to start the BIOS from RAM. In case of BIOS, we will concentrate more on BIOS here. BIOS is a software running in special mode called real mode, meaning no virtual memory here. Once the BIOS starts, it will perform a hardware check. The BIOS then attempts to find a bootable device by checking the configured boot order, which typically includes devices like hard drives, optical drives, and USB drives. All right, so BIOS is, so what is the BIOS? It's the old school firmware. It loads the master boot record from the first 512 bytes of the boot link. All right, has been around 40 years. And UEFI is a modern replacement for BIOS designed by Intel. So it supports, so it's something modern. It's similar to BIOS, but something modern. Bootloader stage, reading the master boot record. When a bootable device is selected, the BIOS will read the first sector, which is 512 bytes of the device. Well, the things that we mentioned in our script, if I'm not mistaken. So this is the master boot record, and these are the disk partitions. So what is the MBR containing? It contains the bootloader code in the first 446 bytes. Then the partition table for that disk. Let me also write this. I think this could be useful and interesting. So we have the bootloader, the partition table, and the boot signature. Okay. To determine if a disk is bootable, the BIOS looks for the boot signature at the end. So if I would do something like this, I don't think this will work. Boot pin. Yeah, this won't work. And then we have yeah, I think I bookmarked this program counter. To determine if a disk is bootable, the BIOS looks for the boot signature at the end of the first sector. Essentially, it indicates the presence of a valid partition table format means. So the grub is too large to fit in the first 446 bytes. So we will use an alternative 3-stage bootloader process, and only the first stage is present in the MBR or the master boot record. Which makes sense. So this first stage, contains pointers to future stages. So we have stage 1.5, which has 32,000 bytes. It contains file system drivers, am I right? And stage 2 contains file system drivers Well, so can just stage 2. Alright, so after the stage 1.5 is loaded into memory, it has the necessary file system drivers to locate and load the stage 2. Stage 2 is loaded in memory from the boot directory using a full Linux file path. Ah, so this is the stage 2. So this is the grab menu. Alright. It allows the user to select an operating system or kernel to boot. If no selection is made, grab will then load the default configuration from menu. Alright. And then we load the kernel. Okay. What are init frames? Init tram fs. It contains all essential drivers and modules the kernel requires to mount the actual root file system. And then we have the user space. Alright, so we run init or systemd from init ram fs. Right, init ram fs. And then we switch to the real root file system. So what else do we have here? Yeah, it's very informative. Very informative, but I think I also have something. I should have something written here. Just a second, let me close all of this. I think I also have a video here somewhere. How does the Linux boot?
What really happens behind the scenes when you press that power button to boot up Linux? Today I'll give you an inside look. The process starts when you press that power button to turn on your computer. First, a program called the BIOS or UEFI boots up. These are basically pieces of software that get all the main parts of your computer ready for action. We're talking about the keyboard, screen, hard drives, and so on. UEFI is the newer kid on the block, offering faster boot times and better security features like secure boot compared to the traditional BIOS. One key difference between BIOS and UEFI is in their approach to disk storage. BIOS is tied to the master boot record system, which limits disk size to 2 TB. UEFI, on the other hand, uses the GUID partition table, removing these size constraints and offering a more flexible and modern solution. Next, the BIOS or UEFI runs a check called the Power On Self Test, or POST. This test makes sure all the different hardware bits and pieces are working right before fully turning everything on. If POST finds a problem, it will often show an error message on the screen. Now finally, if everything checks out with POST, the BIOS or UEFI needs to find and load up the bootloader software. The bootloader is usually set to check the hard drive first, then USB drives or CDs if it doesn't find anything on the hard drive. You can customize this order in the BIOS settings if you want. On a BIOS system, the bootloader code lives in the first little chunk of the hard drive called the master boot record. For UEFI, there's a separate partition that stores files like the .efi bootloader file. The key jobs for bootloaders are locate the operating system kernel on the disk, load the kernel into the computer's memory, start running the kernel code.
Wait, let me go from start.
When you press that power button to boot up Linux. Today I'll give you an inside look. The process starts when you press that power button to turn on your computer. First, a program called the BIOS or UEFI boots up. These are basically pieces of software that gets all the main parts of your computer ready for action. We're talking about the keyboard, screen, hard drives, and so on. UEFI is the newer kid on the block, offering faster boot times and better security features like secure boot compared to the traditional BIOS. One key difference between BIOS and UEFI is in their approach to disk storage. BIOS is tied
So BIOS is the correct way to say it.
to the master boot record system, which limits disk size to 2 TB. UEFI, on the other hand, uses the GUID partition table, removing these size constraints and offering a more flexible and modern solution. Next, the BIOS or UEFI runs a check called the Power On Self Test.
A century ago, humans
this test makes
split
sure
the atom.
all
Now
the
we
different
need
hardware
to
bits
use
and pieces are working right before fully turning everything on. If POST finds a problem, it will often show an error message on the screen. Now finally, if everything checks out with POST, the BIOS or UEFI needs to find and load up the bootloader software. The bootloader is usually set to check the hard drive first, then USB drives or CDs if it doesn't find anything on the hard drive. You can customize this order in the BIOS settings if you want. On a BIOS system, the bootloader code lives in the first little chunk of the hard drive called the master boot record. For UEFI, there's a separate partition that stores files like the .efi bootloader file. The key jobs for bootloaders are locate the operating system kernel on the disk, load the kernel into the computer's memory, start running the kernel code. Now, some common bootloaders you might see are Lilo and grub2. Lilo, or the Linux loader, is pretty outdated and rarely used in modern distribution. grub2 is the most full-featured and widely used today. It can handle booting multiple operating systems, looks nice with graphical or text-based menus, and has a bunch of advanced options for power users. So once grub2 loads itself up, it inserts the Linux kernel into memory and hands control over to the kernel to finish the startup process. After the bootloader starts the kernel takes over the computer's resources and starts initiating all the background processes and services. First, it decompresses
Yeah, so I wanted to say this. So installs the drivers
itself onto memory, checks the hardware, and loads device drivers and other kernel modules. Next, an initial process called init kicks off, which in modern Linux systems is typically systemd. Systemd has replaced older init systems like sys5 init and upstart, and is the parent of all other processes on Linux. Systemd has a ton of responsibilities to get the system booted and ready to use. It's checking for any remaining hardware that needs drivers loaded. It mounts up all your different file systems and disks so they're accessible. It starts launching all the background services you need, like networking, sound, and power management. And it handles user logins once you get to the graphical prompt, and it loads up your desktop environment with the panels and menus. Systemd uses target configuration files to decide which mode it should be booting into. Something basic like multi-user text-only target or the graphical target most of us use daily. Those targets kind of corresponds to the old run levels from past Linux days, if you heard of those before. Mostly now, you just need to know systemd handles initializing everything that needs to launch behind the scenes when starting up Linux. And there you have it. We've unpacked a sequence of events that transform your computer hardware into a functioning Linux system when you press the power button. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 500,000 readers. Subscribe at blog.bytebytego.com.
Oops. Let me take another look. Let me take another look at another video.
Hello and welcome to Source Dive, where we take an in-depth look at some of the interesting low-level open source projects out there. Okay, so to really kick this off, this series, we're going to start off with something called XV6. XV6 is a Unix-based operating system that is kind of used for teaching, right? It's the basis of a whole bunch of operating systems undergraduate courses. And yeah, like I just want to highlight here the GitHub page. It's under MIT PDOS, and this is the XV6-RISC-V. So we're going to be looking at the RISC-V variant. There are various variants of the XV6 operating system. We're going to be taking a look at RISC-V. Okay, so XV6 is a re-implementation of Dennis Ritchie's and Ken Thompson's Unix version 6, which was just V6. XV6 loosely follows the structure and style of V6, but is implemented for a modern RISC-V multiprocessor using ANSI-C. Okay, so there's a bit going on there. This is a re-implementation of the original Unix, or the version 6. Of Unix, so once it had matured a little bit and gotten through some of its initial periods of building abstractions, this is based on the actual code by Dennis Ritchie and Ken Thompson, so you know it's actually going to be pretty good, as they were fairly good programmers as things go. And this is actually implemented for RISC-V, so there's going to be a bunch of RISC-V specific things in there, although of course this is an operating system, so at some level, you know, there's a bunch of code which is agnostic, and there'll be some code which is processor specific or architecture specific. It's multi-processor. That means that this is a...
By the way, Dennis Ritchie is the genius who created the Unix operating system and the C programming language. With Ken Thompson, I'm sorry.
Multi-core system. We are actually going to be running with something that more than one CPU, and because of that, there's going to be a whole bunch of things inside the operating system that have to be aware of that. So that's, I think, quite interesting. If you haven't played around with kind of, yeah, the idea of having multiple cores at the same time is quite an interesting one. And ANSI-C. So this is implemented using very standard, you know, very kind of, I don't know how, not modern C, what we would call modern C, but ANSI-C. So sort of like the very broad variant that is well known by almost everyone. So that's what we're going to be doing, and kind of the point of this series in general is basically to really get good at programming, you have to write a lot of code, but you also have to read a lot of code. And I think that is one of the points where people fall down a little bit, especially beginners and intermediate programmers. I think don't realize the importance of reading code versus writing it. And I think it's kind of obvious why that's a good thing, right? It forces you to, like learn about new ideas that you haven't come across before, but also just different ways of structuring, different ways of solving problems that you might not have thought of yourself if you spent 5 years just writing things. Because sometimes,
yeah, definitely reading code, not reading code, is extremely detrimental to your success as a engineer. Only, if not only for the added benefit of seeing another person's perspective, but also to understand, to get the kind of the sixth sense of what has been done. And I remember for me, because I was working 8 years with Angular and React, I can see an MR, a merge request, and I can just glance at it and kind of understand, oh, so this is the big picture. And I can glance at it and see, oh, maybe this can be an underlying bug or something like
sometimes we get
this.
stuck in our own little, ruts, our own ways of doing things, and kind of stepping out of the box, reading other people's solutions is a really good way of getting around that. And in my opinion, it's a really good way to level up. So that's what I like to do myself. That's what we're going to do in this series. And I've been studying this code base for the last couple of weeks, the XV6 RISC-V code base. And I have to say it's really beautiful. I really like it. And it's the first time I've really come face to face with any operating system code. The first time that I've really dived into this kind of stuff. The first time I've really looked at multi-processor kind of systems at this low level. So yeah, this is quite an interesting one. And I just want to share kind of what my process is of kind of approaching an unfamiliar code base, how you can kind of find your way around. And yeah, and let's explore this code. So without further ado, let's get into it. The first thing you're going to want to do is to actually clone the code, right? So you want to come over here, you want to click the code button, and you want to download this so that you can open it in your own editor. You don't want to be trying to explore code on GitHub itself. Now, yes, GitHub has improved in the last couple of years. Yes, you can get a lot of information through their standard interface. They also have kind of an online code sandbox interface. That's also
Recently, I realized that GitHub has an option in which it references code declarations like variables and functions, and it's really helpful. It's really good. Again, it's not an IDE, it's not a real editor, and it's slow. It's painfully slow, but it's actually quite useful. Again, as
also great.
the author suggests, I also wouldn't suggest reading code on GitHub.
I would say download this, open it up in your own editor with your own editor settings, your own key bindings, all of the familiarities that you have there, because that's going to give you the best chance at kind of really getting to grips with the code. You arm yourself with the tools that you use every day to actually understand code that you and your colleagues write. Apply that same thing when you're reading code to learn, right? It's the same idea. Treat it like any other code base. So let's switch over to the code view. And so we're here in VS Code. I've downloaded the project, and it looks like there are a few files changed. It's really only me removing empty white space from the end of lines, because that drives me crazy. It comes up as a red, like a red thing on the end of the line on this editor, so I like to fix those. But the code is just as it is now. I haven't really changed anything. So we have a couple of directories inside the project. We have the kernel. There's a whole bunch of stuff here. There's no kind of folder structures. We've got a whole bunch of header files, C files, assembly files. And it's kind of overwhelming, I think. If you come into a project, this is actually a relatively small project. And if you come into this and you see this number of files, it's kind of hard to even figure out where to begin. So we're going to look at my techniques for doing that. There's another little directory here called MKFS, make file system. There's a single C file in there. That's really about building up the file system for this operating system. So there is a file system that gets created, and kind of we can pass that to the environment that we end up kind of creating to run this operating system. We'll look at how we build and run the operating system in a moment. Finally, there is a directory of user programs. So these are the user mode programs. This is kind of like the system software that you expect, right? Things like mkdir, make directory, and things like printf, and the shell, and malloc, the user malloc, so memory allocation. So this is basically a whole bunch of utilities that you can expect to run on your operating system. All right, so that's kind of how it is. Let's actually build the project and take a quick look at just a quick look at running it and get an idea of what we're even dealing with here. So to build this, you need a RISC-V toolchain, and getting RISC-V toolchain set up is not always trivial. It can actually be a little bit of a pain, and for that reason, I have packaged up a RISC-V toolchain, a very general RISC-V toolchain that can do all the various flavors of RISC-V, 64-bit, 32-bit, the various extensions that you can have. I've packaged those up into a Docker image, and I'll leave a link to that image where you can download it in the description of this video so that you can use my own Docker toolchain for this. So what we're going to do here is we're just going to run make inside Docker. So what that's going to do is open this whole project up in Docker that has a RISC-V toolchain and build the project. It seems a bit crazy overkill to do this, I do understand that, but it's a good way of making sure it's reproducible. So we're going to run the build. This is the real-time build. The kernel has been built. All of the user system software has been built. It all gets linked together, and then everything is kind of ready. So if we open up the kernel directory now, you'll see that there are all these extra files in there. So there's like a
All right, so most probably everything has been compiled, and there wasn't a trivial way of doing this. So most probably the author grouped together a bunch of commands in order to compile all of these files.
.d file, there's a .o file. There is a kernel.sim, which is all of the kernel symbols that we can use that got assembled. And there is a kernel.asm, which is kind of an assembly dump mixed in with the C code of the whole operating system. So this is kind of quite a useful thing to do when you're debugging. This is a good debug strategy to take advantage of. All right, let's actually run this. So in order to run this, we need to run this in QEMU, the QEMU emulator. So it's basically a way of running kind of virtual machines, emulated machines. And you can do it with all different kinds of architectures. And yeah, basically this project is kind of targeting a virtual QEMU machine. But that machine has kind of virtualized hardware for things like disks and all the kind of various like supporting hardware that you'd have around the CPU, like an interrupt controller and all of that kind of stuff. All of that is actually built into the emulator. So to actually port this over to real hardware is quite possible. It's quite doable. You would have to do.
All right. So first of all, it's called the QEMU, right? And basically, as he said, it's just a way of virtually allocating different resources, so to say, quote unquote, resources, in order to run and compile these operating systems. And most probably the author will say something like, oh, you can also do this on a real machine, but on a real hardware, but it will take considerable amount of time, more time than
some work, but not too much. Like it's not too far off what a real computer would be. So in order to do this, we're going to run make QEMU. We don't do this one inside Docker because QEMU, I just have it installed on my system. You can quite easily install QEMU on the system. It's kind of out of scope to go into how to do that now. But I'm going to run that, and it looks like we're missing the file system image, so we need to build that. So I'm going to do, again, running inside the Docker container to make the file system image. It goes ahead, it's going to do that, and we should be able to run make QEMU now. And what we can see here is, and maybe I'll just clear the screen first before we do this. Okay, so we run this command, QEMU system RISC-V64, a virtual machine, no BIOS kernel. This is the built kernel that we have that gets built from this directory. This is the amount of memory that we have, RAM memory, 128 megabytes. SMP, symmetric multiprocessor, 3, I think that stands for symmetric multiprocessor. We have 3 CPUs in this. We can run up to 8 by default in XV6. No graphical, and we're emulating a disk drive, so that's what that last part all goes into. All right, so what we can see is we get a message that says the XV6 kernel is booting. We see another message that says Heart1 starting, Heart2 starting. Then we see.
If you remember that mini kernel that we wrote, I mean, it's not even a mini kernel, it's only the first section of a bootloader. We had a same QEMU system, but we use x86, if I'm not mistaken. This one is for RISC-V.
We see that init is starting the shell, and you can see that we have a shell prompt here. And if I run the ls command, you can see we kind of get a kind of Unixy, Linuxy output here for ls. So there's a readme, and you can see that basically in here are all the programs that get run. So there is an echo, there is a cat, there is a grep, an init, a kill, symbolic link, list, remove, start another shell, stress test, user test, grind, word count, and zombie. So we could do something like run word count on the readme file. It tells us that there are, what is that, 2,305 characters in the whole thing. Should we cat the readme file out here? So this is actually just the readme file that is in the Git repository itself. I think it's just this readme file. So we can see it prints that out. And what else do we have here? Let's just run one more command. We can take a look at stressfs, or I haven't really run a lot of these commands, I have to admit. Maybe we can try grep. So let's try cat readme, and then we'll run grep. And let's try, well, I can see there's a line there with you, so let's try that. You will need RISC-V new lib chain from. All right, great. So that's how it works, and I'm going to run Control-AX to get out of the machine, to kill the machine. So that's kind of what we're looking at here. It is like a little virtual computer, and we can actually run multiple processes at the same time on this computer as well. So without further ado, let's actually look at some of the code, because that's kind of what this series is about. It's not so much about kind of exploring the project itself in like a very practical sense. Let's actually look at the code. So where do we even start with this? I'm going to run make clean to get rid of all the built files. Where do we start with this? Well, there's a whole bunch of files in here. One of them is a linker script. And for a really low-level project like this, if you have a linker script, it's actually a pretty good place to start, because it's going to tell you like what the entry point is. So if we open this up, if you're not familiar with linker script, I don't blame you. It's kind of one of those obscure things that like people don't usually spend a whole lot of time on. Because I've worked quite a lot in embedded recently, I'm quite familiar with linker script, so I've done a lot of work with linker script. So I know that, for instance, we will specify here what the entry point of the program is. So apparently there is somewhere a function or a symbol called entry and underscore entry, and that's going to be where the program starts. So that's a really good place for us to kind of begin exploration. And then there is a little bit more going on here, standard linker script stuff. This is actually a really clean, basic, straightforward linker script compared to what I've seen. So this basically tells us ensure that the entry.s/underscore entry symbol is at hex 8 million, where QEMU's kernel is jumping to. So this QEMU virtual machine expects the kernel to be loaded at this address. So that's kind of built into this whole assumption here, and maybe that will come up in various places. Of course, we actually do need to know where various things are in the address space. So there are kind of virtual hardware that gets mapped into the address space. But we know that this is where the kernel is going to be. So that's where it's going to be ending up when we build it. All right, so that means that we can go over to this entry.s file, and this is where it actually starts running. So this is kind of our beginning entry point. This is where everything goes. So in an operating system, really in any kind of project, in an embedded project or whatever, arguably, the first thing you want to do is to get out of assembly as quick as possible. Like, especially for an operating system, and also embedded projects themselves, you basically have to start in assembly. There's no, like, you can't like immediately go into C, because there are things you have to do to set the environment up so that C can even run. You need to have something like a stack in order to make function calls and push variables onto the stack. So that's the very first thing we end up doing here. So what we do, if you're not familiar with assembly, and especially not RISC-V assembly, what we're doing is we're saying that this stuff here is going to go into the text section. The text section, in terms of assembly and building code and running compilers, the text section is where the code goes. So that's, I don't know why it's called the text section, but that is what it is. Then we're declaring here a global symbol called entry. So the symbol is available to everything around in the program. And here we are, we've got entry. And we've got a little comment here. This comment says, set up a stack for C. So we want something where we can make function calls and not lose our state as we kind of do various function calls. Stack 0 is declared in start.c. Okay, so that also gives us a little pointer to where we need to look at next. So we can actually open up that file already. We won't do something with it yet, but I'll just leave it open there. So with a 4096 byte stack per CPU, so that's 4 kilobytes of stack space per CPU. And we can actually work out what that stack pointer needs to be based on the
What is stack space?
the address of this stack 0 variable, which we'll take a look at in a second, multiplied by something called the heart ID, multiplied by 4096, which is the size of that stack. So let's just take a quick look at.
So the stack is a region of memory that your program uses for storing temporary data, function calls, and returns local variables and saving register state. Ah, so it's a stack, like the data structure, right? But the stack space is... so it pushes value and it pops values. All right.
Stack 0. If we open up start.c and we sort of scroll around, you'll notice this line here, and also a comment that mentions entry.s above. This is basically us just assigning some memory to be the stack space that we're talking about here. So the way that compiling programs works, if you're not too familiar with it, the way that compiling programs works is you kind of compile all the individual units separately. So this entry.s, that's going to be compiled on its own. And this start.c is also going to be compiled on its own. And what will happen is there may be references to other places in the program that aren't actually part of your little module that you have. So this stack 0, it doesn't actually exist here in this file, but it does exist somewhere, and that's what we're saying. Like, it should exist. And then there's a second step. Once you've built all of your objects, once you've built them all, then you come in and link them all together into your final program. And that is the step where kind of you resolve this idea of like, hey, I actually mentioned the idea of this symbol. Is it anywhere? Is it in any of these units you've given me? Oh, it is. It's over there. Great. And then we can sort of link those two things together. So that's what's happening here. We've got some memory space devoted to stack 0. And all this is actually is a character array. So it's an array of bytes, essentially just bytes. And how many bytes are there? There are 4096 times the number of CPUs. And this NCPU, that is just a constant macro that is the maximum number of CPUs. And apparently that number is 8 in xv6. So if we just kind of go to the definition of that, we open up this file called param.h. So we're kind of spidering our way out through the code base by doing this, just exploring and seeing like kind of what is this piece referring to.
This is actually a really common way of looking at understanding code bases. I remember I'm doing some minor work in reversing Android dApps, and you always open something similar to entry.s. You check in Android manifest what is the starting position, then you kind of circle around, you look around. So it's somewhat similar to this.
This is why
only this is like done on a low level.
You want to do this in your editor, by the way, because your editor has the ability to kind of resolve these symbols, and you can use the facilities of the editor to say, this thing is mentioned, like, where is it? Tell me where it is. So the number of CPUs is 8, but you can see that there's a whole bunch of things in here which are described, like the number of processes which can run on the machine, the number of open files per process, which is possible, that's apparently 16. The number of open files that can be in the whole system, that's 100. So this file, param.h, is kind of a parameterization of the system. You can come in here and fiddle with these values to get to something that makes sense for whatever you're trying to accomplish. But as we'll see as we go along, is that these numbers, if you change them, you can't just say, oh well, let's make a really massive let's say that we can have 1,000 processes. Like, there is a cost associated with that, because actually for every process in the system we pre-allocate memory for it. So there is always memory dedicated for 64 processes on the system. Whether or not we run one process or 64, there is a full 64 process worth of space. And we can see that here in the stack sizes for the CPUs. Even though when we ran QEMU, we only ran with 3 CPUs, there is space for 8. So that's something to consider as you're kind of fiddling with the numbers. But in the end, we end up multiplying, basically having 4096 bytes per CPU in one big flat array here. And that's what we're referring to inside this comment. So let's kind of unpack ourselves a bit. What are we actually doing here? This instruction is load an address into the stack pointer. So RISC-V has a bunch of registers, general purpose registers. And there are 32 general purpose registers. One of them is hardwired to the value 0. So if you refer to it, you will always get the value 0 back. And if you write to it, nothing will happen because it's always going to have the value 0. That turns out to be really useful. But yeah, this instruction that we're doing now, we're loading the address of this symbol stack 0 into the stack pointer. So that's kind of our starting basis for this, even though we eventually need to get to this whole equation, right? That it's stack 0 plus the heart ID, whatever that may be, times 4096. Okay, so the next thing we do is we load an immediate value into the A0 register. It's just another one of the registers, and what we're loading into that is 4096, right? 1024 times 4. I'm not quite sure why they didn't just put this constant in here, but either way it's fine, right? We know this value. So A0 now contains 4K, and SP contains stack 0, so we just need to do this heart ID multiplied by this A0 now. In order to do that, we run this next instruction, which is CSR read, and the CSR is a control and status register, and a control and status register in RISC-V is a system-specific specialized register that isn't a general purpose register. You can't use it like you would use here the stack pointer in every instruction. You can only use the CSR values in CSR instructions. So what we're doing is we're reading into the A1 register the special CSR M heart ID. And what is a heart ID? Well, a heart ID is the hardware thread ID. And that's basically a core, right? It's the index of the core that we're running on. Remember, this is a multi-core system. We can have up to 8 cores. So basically, this is going to give us the unique ID of this core. And because of the way that, well, especially in this implementation, but generally as it works for systems that build multi-core systems, like if you have a chip that implements multiple cores, they will generally they will be sequential, right? So it will go from 0, 1, 2, 3, 4 onwards, maybe starting at 1, maybe starting at 0. So this is going to read us the heart ID of this system, right? The core ID. So let's imagine it's 0, for instance. This is the first core. So what we do is we add 1 to that, right? That's in A1. Then we're doing an add immediate. Result goes into A1, and it's A1 plus 1. So we're adding 1 to that. We'll get into why we add 1 in a second, but then we end up multiplying A0, which contains this 4K, and we multiply that by this value that we just placed in here, which is the heart ID plus 1, and then we place that back into A0.
Why?
And then in the end, we add to the stack pointer and place it back into the stack pointer this A0 value. So effectively what we've done is we've
stack 0 is declared in start C. A0, no idea what it does. All right, so this control, what did he say this is? All right, so he sets this heart ID in this A1. We add 1 to A1. We multiply this, and then we most probably we spread it by the address.
We've completed this operation now, right? The stack pointer now contains the beginning of the stack plus the heart ID multiplied by 4k. It's actually the heart ID. It's actually the heart ID. Apparently, doesn't work here. Plus 1 multiplied by 4k. And the reason it's plus 1 is because a stack in memory, it actually grows downwards. So what you want to do is you want to say that your stack begins at the high point and you're going to grow it towards sort of the beginning address as you go down. So by saying that we are starting at stack 0, right? And if we call 0, that's stack 0 times 4k, so plus the heart ID times 4k, so that's just, that at that point that is just stack 0. Then we're adding another 4k to that whole thing. So we're starting at the top, and then we have a stack that can grow downwards for the core. I hope that makes some sense. And then finally, now that we have a stack set up, we can actually jump into C land. We can move our computation into C, where our expressiveness goes up a lot, right? We can start to express programs a lot more straightforwardly. So then we call this function start. And after that, you can see that there is just this little infinite loop down here where we have a label called spin, and we just jump to the spin label. So we'll just stay on this instruction forever if we ever end up here. And we don't actually expect to ever end up here, right? This is just a kind of safety net, because this function should never return. We should never end up back kind of returning from this function.
All right.
If we happen to return, then we'll just spin forever. So that's kind of just a safety mechanism.
This is what I wanted. So what's this? This is the entry.s, and it's located inside the kernel. So they updated the comment according. This is what I meant. The references in GitHub. Okay, let's go back. Right. So as they said, this is the RISC-V assembly code. It's the first thing executed when the kernel boots, and this entry function is our entry point. The BIOS jumps exactly. This is the BIOS reset vector for our kernel. So this one creates a label called entry in the text section, which is the code section. This is the global one, so the linker can use it later when we link as a entry point. I think he said so we add the address of the stack to the SP register, right? The size of the stack is 4 kilobytes, and I added to A0. A1 is the heart ID from the core ID, read from the machine CSR. All right, we increment the heart ID here, so 0 gets its own stack. We create some offset, and our final SP is stack plus offset.
Okay, so now we can move on to start.c, And this is kind of going to be the last thing that we cover in this video. I think it makes sense to pick up a little bit more of the system in the next one. But basically, in start.c, what we're actually doing is setting up the environment ready to get the system up and running, right? Ready to actually begin running the operating system. So we're still kind of very low level and very processor specific while we're in start.c, but we've kind of, we've bumped our abstraction level up a little bit. So what are we doing in here, right? Well, as we've seen, we have this this variable for the stack. We're actually using that now as our stack space. Another thing to keep in mind is that this code, and the code that we just saw in entry.s, is running for every CPU, right? So if we have 8 cores, all 8 cores are running the same code at the same time. And kind of the way that you can differentiate those cores is the fact that we can access the core ID that we're on. So we actually can make it do different things based on the core ID. But right now they're all running the same code, except for the fact that they all have their own individual stack. So they can all make their own individual calls, they can all have their own individual variables. So we also, below here, we have some kind of timer data structure going on. It's called timer_scratch. And we have an array for every CPU. We have 5 uint64s. So this is a 2-dimensional array that has the core index here and sort of 5 values that we can store. We'll get to those a little bit later. What we actually want to focus on is this start function, this void start. So entry.s jumps here in machine mode on stack 0. Okay, so this is where we're going to start executing code. So something to note is, in RISC-V, and indeed all complex processors that are able to run modern operating systems, you have the idea of different privilege levels. So the core can be running at an extremely high privilege level, say machine mode, as it's called in RISC-V, and in machine mode, you can just do everything. You can access all of the resources, you can access every possible register that's available, every CSR, the control and status registers. You have access to the entire system. But in fact, you don't want to run your even your operating system code at that highest level of privilege, because it's just sort of unnecessarily dangerous and exposing your system to corruption, not even through kind of security concerns, but just through faulty software running. And as another note, often these days modern operating systems don't actually run on like the highest level of the system, because they're often virtualized and they're not even real operating systems. So they're running inside another operating system. So they you need to be in such a place that your software runs at a level where it doesn't have to believe it owns the entire machine. So that's kind of like a useful thing to know. So in RISC-V, we have the machine mode level of privilege. The next level down from that is called supervisor mode. And in supervisor mode, that is where you would run an operating system. So that is still a very high level of privilege in the system. You can do a lot. You can set up all kinds of different things. You can have interrupts. You can have exceptions. So all kinds of traps. You can deal with timers. You can deal with setting up memory privileges in some cases. And you can also set up virtual memory. So that means that you can do memory mapping. Virtual memory mapping is in like an instruction fetch happens and it goes to go from address 123, but address 123 is actually mapped to some other physical address on the system. And the reason that we do that, of course, is so that multiple user processes can all think that they have a unique view of the system, but they're all kind of in a self-contained box that is actually, only some tiny constrained version of the actual system. And of course, that means that one process can't accidentally write to another process's memory because they're physically not mapped to each other, right? There is no access from this place to this place. So that's kind of what virtual memory is all about. And the supervisor mode, it can do all of those things. So it's able to control all of the virtual memory. And finally, below supervisor mode, there is something called user mode, right? And that is where you actually run processes and user processes. That's what we would expect kind of normal code to run on. And that is the lowest level of privilege. We can't do all the normal, we can't do all the very low level things in the system, like, taking interrupts and writing to arbitrary memory locations, changing the way the virtual memory works. We're very constrained. We can only run in a small environment. And if we want to go outside of that environment, we want to do something more complicated, like talk to a piece of hardware, then we have to actually make a request to the next level up in the system, the supervisor mode. We need to make a system call into the supervisor and ask it to do something for us, like open a file. And then the system will go and take care of that, the operating system, and it will give back some result to the user's process. Okay, so what is this start function actually doing then? Well, the idea of the start function is to get us out of this highest level of machine privilege and into the supervisor level of privilege. But before we can actually do that, we need to set up a few things in the machine mode, things that we can only do while we're at this highest level of the system. So this is a little bit RISC-V specific, this part. This is still it is especially RISC-V specific in that we're writing to, RISC-V related registers. But it's also relatively general in that you would probably need to do these same kinds of things on any other type of system, but they just wouldn't manifest in the same way, right? There would be different specific steps you'd have to do. So what are we doing? The first thing we're going to do is to write into the M status register, the machine status register, and we're going to set the bit that says the place where we just came from, the previous privilege level that we came from, which we didn't come from anywhere, we've just started the system, but bear with me for a second. The place where we just came from is going to be supervisor mode. We're going to manually set that, and that's what these lines are doing here. First, we just read the current machine status register, and I'll show how that works in a second. Then we are clearing the bits that represent the machine privilege, previous privilege, and then we are setting those cleared bits to be the supervisor level of privilege. So that's kind of what all of these specific things are doing on these lines. I'm not going to go into how these bit operations work, because this is bit operations that are taking place here. I've talked about that a whole bunch before in videos, and there are a whole bunch of good resources for that as well. Finally, we write that back to the status register. So all we've done here is to go in and set up that the previous privilege level where we came from is supervisor mode. because our end goal is going to be to kind of trick the system into taking us back to a different place. But of course, we never really came from anywhere. We're just kind of we're setting it all up as if we were coming from that place. So next up is setting up another register.
So just to reiterate, the entry.s guarantees that each CPU gets a separate 4 kilobyte stack so they don't stomp on each other.
Called the MEPC, the Machine Exception Program Counter. This is like where we have the MPP, the Machine Previous Privilege. This is kind of like the previous place we were executing, the physical address where we were executing. So we're just setting that to be a function called main. And main here, we've got like a declaration that there is some function called main somewhere. But if we kind of right click and open this up, we'll actually come into this main.c file. And this is like the actual beginning of the operating system. You can even see here this message with a printf, xv6 kernel is booting. Well, we saw that earlier when we ran the operating system. So this is kind of like the actual setting up of the operating system. So the end goal is that we get to this point. But still, in start.c, we have a little bit more work that we need to do. Let's actually take a look at some of these functions here. Like, so this r_m status, well, that stands for read the m status register. So let's take a look at that. That brings us to this file called risc5.h. And risc5.h just contains a whole bunch of inline functions, which are basically, as you can see, just assembly instructions. So there's just like a single assembly instruction that's happening inside this function. So it's not even
Okay.
a real function, actually. Like, this is going to become inlined, and it's going to become inlined in such a way that it translates to basically a single instruction. So this is quite interesting. Like, this is something that we need to do. It's kind of a bridge between C and the assembly world. We sometimes still need to do these really specific C, like processor-specific things, but we want to do them from the world of C, right? We don't want to still do all of this stuff in assembly. We could, but it's still nicer to do all of this in C. So what all of these instructions do, like for instance, read the m status register, well, it basically executes a CSR read of the m status register and ends up putting it into this kind of generic register that happens. This is special syntax for C for doing inline assembly, and there are ways that we can basically say, hey, run this instruction and kind of get it to like treat this register, which we haven't specified, get it to treat it as this variable. So we have a variable in C, but we can kind of cross it over with the assembly and say, well, when you read this value, kind of stick it into this variable, and then we return that variable in the end. So this is the way in which we can like cross the bridge, right, between assembly and C. And likewise, we have the equivalent write m status that takes in an x, and what we end up doing is a CSR write of the m status register with this generic thing, and of course that generic thing that we're trying to do is this x value. So we're in this case injecting the value instead of extracting out. And all of those work the same, right? So the write_MEPC, that does exactly the same thing. This is our x. We end up injecting that kind of into an assembly instruction. And next, after that, after we kind of set up these two pieces, which are just saying that eventually when we drop down, we want to drop back down into the supervisor mode. This next part is kind of doing a little bit of setup on the supervisor mode. So we're going to disable paging. Paging is to do with virtual memory. And this register here, the SATP, or the supervisor address translation something, I don't remember what the P stands for, but it's to do with address translation. We're writing a 0 into that. And basically what that does, it turns off virtual memory. So when we end up in the supervisor, we're still, like every address that we talk about in the system is still a regular old physical address. Like if I say 123, it means 123 in the system. I think by default, in almost every implementation, virtual memory would be off by default, but this is kind of just like a, let's make sure it's off kind of thing. Okay, next up, if you read the comments, it also explains a lot of what we're doing here. We're going to delegate all of the interrupts and the exceptions to supervisor mode. So interrupts and exceptions, they're like a very core low-level thing that happens in operating systems and happens in, on processors in general. Interrupts are things like...
Oh, I need to stop it here. I need to stop it here. We are going to continue with something else. You know what? I'm on a roll. Let's continue. Let me show you my tablet again. Here it is. Let me also show you my cool wallpaper. I might change it soon, but the thing is, I stopped at last time. I didn't do a lot of explaining, but I wanted to talk about underfitting and overfitting. At least I wrote underfitting and overfitting right here. Now, as I said, let's say these are our points, these are data sets. And this parabola type line that we have right here, the line in blue, it's actually perfect. I mean, it's not perfect. We might find a way to make it fit even better, but the shape of it, it's perfect. And what we could do apart from this is, for example, instead of using a degree of 2, maybe we can do something like this. I can do this, and 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 this, which would be a polynomial of degree. So what is 1, 2, 3, 4, 5, 6, 7, 8, 9? So it's a polynomial of degree 9. Let me go back. So I could also write a simple line like here, but there's no way I could find a good line that fits well here, because the dataset simply does not look like a line. So a line is basically underfitting our dataset. Our parabola works pretty well. It's not overfitting, it's not underfitting. Now, our line with the degree of 10 that manages to go through each line, it actually captures it, but it doesn't project the data properly. Because if you do this, we just have a line that follows the points. It doesn't tell us what happens with the data. So we need to find a model that is just perfect. It's not too simple, it's not too complex, and it also explains the data pretty well. So we could actually see this visually. We could see these points forming somewhat of a parabola shape, so we could draw it and we could say, this is the shape that this follows. But what if we have more complex data? What if we have something that's not visible by the naked eye? And especially computers, they don't have the ability to see things and measure them the way we do. So what computers do, they use an error function. So let me just computers use error functions. So we can have the absolute error, or which is the average of absolute differences. And I'm just gonna say maybe in another color. This is the absolute error. And then what's the problem? I want to make this all look nice, but sometimes I'm not tidying up the way I write, or I use too many colors, or my handwriting is not good. So I apologize. So another error is the squared error, or the mean squared error. Again, I have here the y at I minus the predicted value, and it's squared, and I'm gonna name this the square error. Now, the issue that computer make, and now I realize this is too tightly written, but I can fix now. Zero error for the computer means it's a perfect model, but we have a zero error here Every time I draw it worse and worse. We have a zero error here, and this model is too complex. If we get new data, it will fail. It will definitely fail. So the computers optimize only training error. We need to check against unseen data. And if we don't, the model will happily overfit. And maybe, wait. Is this working? Yeah, this is the housing prediction snippet that we did. I'm just gonna add a new one. I'm just gonna add a new one, and let me do something here. Import. Do I have numpy here? At the top, I do have, and I have as well SK library. So I'm gonna import everything here. I import numpy SNP from. Wait, I can do this here. From the metrics, let's import mean squared error and mean absolute error. Linear regression, I have this. I also need to import the plot, and another thing that I need to import, sklearn. I need the polynomial features pre-processing, import pol. Why is this red? Because the way I imported was wrong. Polynomial features. And now hopefully we'll have all of these available here. np random seed 0. So what I'm gonna do, np linspace 0 10 20 reshape -1 1. And what else do I have? Why have I, what have I clicked? I took a screenshot like immediately. I put, okay, my bad. Let me just delete it so I don't. So I'm not surprised when I find it the next time. Okay, y is np minus x plus np random normal scale 0.1. Size will be x shape. So what we did here is we made the randomness reproducible because we will have the same kind of data every run. We created 20 evenly distributed numbers from 0 to 10. This will be our input x. And with reshape, we are reshaping it into a two-dimensional array. Basically, wait. Will this work? Print. Yeah. But if I print this now, we actually now have a two-dimensional array here. In the form rows and features, which are these individual values here. Yeah, our true pattern is the sinusoidal wave, and we add some random noise. So if I print y here, I'm gonna get, wait, let me do this, print x, the x uppercase. And if I do, wait, so the sinus of 0 is 0, right? And here somewhere with the, let me just run this again, with the added noise we get around 0.76. Wait, this is not okay. So it's 0.502, and what's my value? 542. All right. So we create some minor noise to make it realistic. And now let's create a helper function. So here I'm going to create a polynomial feature. So this is transforming the x. The model is linear regression, fit x poly y. Prediction is model predict x poly. And what am I returning? Return mean absolute error between y and y prediction. And then I can just run it like model 1. Degree is gonna be 1. 1. Let me add another one. 1, this is gonna be 5, and this will be 15. So if I run here, polynomial feature is not defined. All right, now it is. All right, so here we see, why am I using absolute error? Mean squared error. You basically see that when we overfit, the model is extreme. It memorizes every single data point, and the training error goes to 0. But if we fed it new data, it would perform terribly. Right. So what can we do now? Where's my tablet? It's here. How can we know if the model is overfitting or underfitting the data? So we could test the model. In order to test a model, you need to pick a small set of the points in the data set, and you need to choose and use them for testing the model's performance. And this is called the training set. Once we train the model on the training set, we use the testing set to evaluate the model. In this way, we make sure that the model is good at generalizing to unseen data. All right. So a good analogy of this is if you have been studying for a quiz and there are 100 questions that could be arriving on the quiz. So you take 80 of them to train and then the remaining 20 to test ourselves. We try to answer them without looking at the book. And let's say this model that we have created in which it only has zeros here and it looks something like this. This guy doesn't generalize well with new data. For example, what if new points appeared? And if you take a look at the parabola that's following the points, if we have a new point here somewhere, look where it is compared.